Hi, welcome to Kalike, and in today's session we are going to continue on what we learned in our previous class. We learned about various properties of charges. We learned about positive and negative charges. We learned why do you feel an electric shock? How do these static charges do get transfer, and why do you get an electric shock or you hear a particular sound, right? A cranking sound when you open a car door in a winter or specifically dry weather. We have answered these questions. If you still have any doubts in mind, you can always leave it in the comments. So in order to continue that, we have a numerical. So we will take a numerical that we learned, which will use the formula that I taught in my previous class. What was the formula that you learned? We learned about the quantization of charge. That charge exists doesn't exist in half numbers, it exists in whole integers. That is what we learned in our previous class. So we have a numerical to understand that. We will begin the class with that. So let me read the numerical for you. The numerical reads as, if 10 to the power of 9 electrons move out of a body. So how many electrons are moving out of a body? 10 to the power of 9 electrons are moving out of a body. When I say a body, they are referring to a particular charge. It could be any metal, it could be silk, it could be rubber, or any material for that matter. So some charges are moving out of a body to another body. Okay. So 10 to the power of 9 electrons are moving out of a body to another body every second. They are also saying at what frequency is it happening. So every second 10 to the power of 9 electrons, which is a huge number. When I say 10 power 9 electrons, it means you have 9 zeros in front of 1, which is a very big number, which is more than a billion. More than a billion of electrons are getting transferred from one body to another body every second. So that's the information given in the numerical. What are we required to find out? We are being asked how much time. So here basically you are calculating time. Okay, how much time is required to get a total charge of 1 coulomb on the other body. Okay. So basically imagine this is a metal sphere, there is another metal sphere. From this sphere to another sphere, 10 to the power of 9 electrons are being transferred every second. But they want to charge this metal sphere or give it a total charge of 1 coulomb. Okay, imagine if they are sending, if this body is sending or losing about more than a billion of electrons per second, and this need to be charged for 1 coulomb. Obviously, this tells us 1 coulomb must be a very huge charge, because this amount of electrons transferring every second is not enough. So they still want to charge it to 1 coulomb. So the body needs to be charged to 1 coulomb. In order to charge it to 1 coulomb, what is the time that you would require is the question. So do we know any formula that connects time with the total amount of charge? Not so yet. So I'll give you away the formula. We may not have learnt it so far. Now that if you are a learner who has already finished your entire syllabus, obviously you will know the formula. If not, I'll give you away the formula. So first let's write down what is given. Okay, the data or what is given in the numerical. So the numerical says how many electrons move out? Number of electrons moving out per second. So number, short form, I will write it as n dot. Number of electrons can be in short written as this. Electrons moving out of that body every second. So per second is equal to 10 to the power of 9. So this is the number of electrons moving every second, more than a billion of electrons. Now what is the total charge that you need to charge it to? You need to charge, we need a total net charge of Q. Okay, we want a charge and the wanted charge I will call it as Q, capital Q. Capital Q is equal to 1 coulomb. So we want to charge it to 1 coulomb. In order to charge it to 1 coulomb, what is the time, that is T, required in order to charge it to 1 coulomb. Okay. Now, since you are transferring 10 to the power of 9 electrons every second, or the body is losing, if I call this as body A and metal A, a metal sphere A and a metal sphere B. So metal sphere A is losing about more than 1 billion of electrons every second. So what is the charge on every electron or a proton? So elementary charge or the charge on an electron. So charge on an electron. Why am I finding this? Because I need to know how much charge I have already transferred. Now, so that I know whether I could charge, I have already charged it to 1 coulomb, or how much more do I need. So charge on an electron, that is E equal to 1.6 into 10 to the power of minus 19 coulomb. So it is 10 power minus 19 coulomb. It is not 1 coulomb, right? So therefore, it's a very least number. So every single electron carries this much charge. So what is the total charge that is already transferred per second? Let's see what is the total charge that we have already transferred. If every charge, for example, for every electron that jumps from here carries a charge of this much. So if 10 to the power of 9 electrons or more than 1 billion electrons jump every second, so every second how much is the charge that is being already transferred? Let's find that out. Okay, so charge transferred every second. Charge that is transferred every second, okay, will be equal to charge transfer every second. I call that small charge as Q. Every second is Q is Q by T. What was Q according to the previous equation that we learnt in quantization of charge? Quantization of charge said Q can be equal to N into E, where N is the total number of electrons, which is 10 to the power of 9 here, and E is the elementary charge or the charge on each electron divided by every second, that is 1 second. So this will be equal to N is 10 to the power of 9 into 1.6 into 10 to the power of minus 19 whole divided by 1, because we are transferring it every second. Let's keep 1.6 as it is. Now 10 to the power of minus 19 into 10 to the power of 9. If the bases are same, what are the bases? 10 is the base and these are called the indices or the powers. So the base are same, so you can add the indices. So minus 19 plus 9. So this will be 1.6 into minus 19 plus 10 will be equal to minus 10. It gets a these many. This is the amount of charge that is actually transferred every second. So this is not equal to 1 coulomb yet, but it is much lesser than 1 coulomb. So much is the charge that is transferred every second. Now, if you need to charge it to 1 coulomb, what is the time that is required is the question. Let's figure it out. I will give you a minute to think and then I am going to reveal the answer. Well, I hope you must have figured it out. If not, I am going to reveal the answer. So, the total charge that we need to transfer is 1 coulomb. So, the total charge, total charge is equal to charge transferred every second, which is Q by T, which we have already calculated, multiplied by total time. So, total charge is equal to charge transferred every second multiplied by the total time taken by the charge to transfer it. Okay. So I hope you understand the logic. So what is the total amount of charge? The total amount of charge is you are transferring it every second multiplied by the total time. So this T, it doesn't make any sense. It is charge. The amount of charge transferred every second multiplied by the total time gives you the total charge on the body B or the metal sphere B. So what is the total amount of charge that needs to be accumulated, which is about 1 coulomb. So I'll write it as 1. Charge by time we have calculated it to be 1.6 into 10 to the power of minus 10 into total time. So we need total time. Now I'll bring everything on the left hand side. So this will be T will be 1 divided by 1.6 into 10 to the power of minus 10. So now we need to simplify. In other words, this can be written as, I'll take 10 power minus 10 to the numerator. So minus 10 becomes plus 10. So therefore 10 to the power of plus 10 divided by 1.6. So it is 1 divided by 1.6. I want to get rid of this point, decimal point. So what will I do? 10 to the power of 10 divided by 1.6 into, since there is a decimal point after one place, right? So we have to multiply it with a number that has 1 0. What is the number which has 1 0? 10. So 10 divided by 10. So therefore now this will become 10 to the power of 10 and 10 to the power of 1, bases are same. You can add the indices. So 10 plus 1 is 11. 10 power 11 divided by 1.6 into 10. If you multiply, this becomes 160. So there is a decimal after 1 point. So this becomes 16. So now we have to calculate how much is 1 divided by 16. Let's do it here. 1 divided by 16. It has to be the other way around. 1 divided by 16. Now what will I do? Since it is 1, it can't go. So I will put 0. I will put a point, that is 0 point. So I get 1 0. That is still less. I get one more 0. So here comes one more 0. And then 16, I think 16 6 is 96. So you have 4. Okay, then this becomes 0. Then with that point you get another 0. 16 3s are 48. So we have to do 16 2s are. 16 2s are, I think it is 32. You get 8. And then 16 5s are is 80. So this becomes 0. 80 by 80 becomes 0. So the answer is 0.0625. So what is the total time that is needed? 0.0625 into 10 power 11. Now I need a whole number. I will shift the decimal point. This can be written, since I am shifting it after 6. Okay, it will be, or I can shift it after 62. 1 2 3. So 62.5 into 10 to the power of minus 3. Right? So when I shift it towards the right, I have to put a minus decimal, okay, minus NDC into 10 power 11. So this can be written as 62.5 into minus 3 plus 11 is 8 seconds. So that's a huge number. So these many seconds is what you require to transfer a charge or to charge it to almost 1 Coulomb. I hope the answer, this is a very big number. You should understand the significance of this number. You see it is 10 power 8 seconds. Again, it's close to a billion. So you require billions of seconds to charge it. Although you are transferring such a huge number of charges, more than a billion of electrons every second, even then you would need billions of seconds to charge, to transfer so many charges so that it gets charged to 1 Coulomb. So, the numbers tell you a lot about physics. So, 1 Coulomb must be a real huge charge. I hope you got it. I think we have one more numerical to go and then we'll get on to the concepts for today. So, here is another question that will use the formula that we used in the previous numerical, but a little bit more that probably you might have learned in your chemistry classes. We'll explore a little bit more in physics. So let's take it up. What does the numerical say? The numerical says you are supposed to calculate the number of positive and negative charges. So how much positive and negative charges, that is protons and electrons, is there in a cup of water? So it doesn't give you any information. It only tells you have to calculate the total number of electrons and protons, or the total number of charges, which is Q, capital Q, right? So the only hint that they have given is a cup of water. Okay, water has a particular molar mass and a cup of water has a particular mass also. So therefore, using that, you will have to calculate. That is something you have to remember for numericals like this. Okay, so yes, the total charge is given by the expression Q is equal to N into E, capital N into E. What is capital N? Capital N is the total number of charges or the total number of electrons and protons. Total number of charges multiplied by this. How do you calculate? Now this we do not know. This is question mark. This is something we need to find out. How do you find out the total number of electrons? When I say charges, it could be number of electrons or number of protons, right? So basically the total number of whatever you have, the charge particles. Total number of charge particles. Now in order to calculate, how do you calculate the total number of charge particles? In order to calculate the total number of charge particles, we know that the formula for water is H2O. That means H has 2 protons and this has about 8 electrons. So what is the total number? There are about 10 charge particles, right? So there are about 10 charge particles, which is both electrons and protons. So we say it is total number of charge particles multiplied by the number of molecules in water. Now how do you calculate the number of molecules in water? Okay, so the number of molecules in water is given by the formula number of moles. Okay, number of, these are all the things that you should remember. You learn more in your chemistry classes. Number of moles multiplied by the Avogadro number of molecules. So this is a standard number that you must know. So Avogadro number is a standard number and I hope you know it. But we do not know what is the number of moles. So can guess what is the Avogadro number by any chance if you remember from chemistry? Yes, you guessed it right. So the Avogadro number is 6.023 into 10 to the power of 23 molecules. Okay, but we have to also calculate the number of moles. So the number of moles is given by the formula is mass of 1 cup of water. Mass of 1 cup of water divided by its molar mass. So this is where it all starts. This is something you must know because it is not given in the numerical. If you know this, you can calculate number of moles. If you know number of moles, you can substitute here, multiply it with Avogadro number of molecules. You can calculate the number of molecules. If you know the number of molecules, you know the total charged particles in H2O is 2 positively charged particles, which is 2 protons in H and 8 electrons. So the total charged particles is 10 into total number of molecules in the water. Now if you calculate this N, you can substitute it here where EV is also known, which is 1.6 into 10 power minus 19 Coulomb, which is the elementary charge either on a proton or an electron, and it becomes very easy in order to calculate Q. Okay, so this is something you must know. I will substitute for this and from there we will go on doing the rest of the part. Okay, so now let's calculate the number of moles. In order to calculate the number of moles, okay, number of moles will be equal to the mass of water. Mass of 1 cup of water, you must remember, is 250 grams. Please remember this. And the molar mass of water in a cup of water is also 18 grams. So the units gets cancelled. So if you divide this, divide it using a calculator and tell me the answer. So that will be around 13.88 moles. So the number of moles is 13.88 moles. Now we will substitute the number of moles here, multiply it with the Avogadro number to find the number of molecules. So the number of molecules will be equal to this number of moles, that is 13.88 into Avogadro number, which is 6.023 into 10 to the power of 27. Now use your calculator and see that it will come somewhere around 83.55 into 10 to the power of 23. Now using that we will calculate N, which we require here. N is 10 into number of molecules. So 10 into 83.55 into 10 power 23. So this is 10 to the power 1. If you multiply, this becomes 83.55 into 10 to the power 24. Now let's calculate Q. So Q is N into E, that is 83.55 into 10 to the power of minus 24 multiplied by 1.6 into 10 to the power of, sorry, this is plus 24 minus 19. So 10 to the power of 24 minus 19, if you do, so 24 minus 19 is, this will be 5, this will be 1, so it's going to be 5. Now if you multiply this, find the answer, use your calculator, and let's see what's the answer is. So therefore it is going to be 1336 into 10 to the power of 4 Coulomb, which is huge. Now what I will do, I will shift, put a point here, I will write it as 1.336 multiplied by 10 power 3. If I shift it onto the left, this will be positive charge. If I shift it onto the right, this becomes negative charge. So to the left, if you are shifting the decimal point, it becomes positive. Into 10 power 4. So 10 power 3 into 10 power 4 will be equal to 1.336 into 10 to the power of 7. So that's the total number of charge. And I hope that's clear. Well, now it's time to understand a very important law in electrostatics, which is called a law of force, or force of attraction or repulsion, and which was discovered by a scientist called Coulomb, and hence the law is called Coulomb's force law of either attraction or repulsion. Now before I directly state the law, I want you to understand how did he arrive at the expression for Coulomb's law. Okay, so in order to come to that conclusion of how does the force vary, he did a small experiment. He took a torsion balance. So how does a torsion balance look like? Now there is an enclosed glass surface. So he kept two metal spheres in an enclosed glass surface. So if this is the sphere A, this is a charge. Okay, this is charge Q1. He kept another charge here. Okay, close to it or somewhere to it. Okay, which is pretty close, of the same size. So this Q1 and Q2 were of the same size or same magnitude. This was Q2. So he kept them, they were charged. Now whenever he started charging these metal spheres, now he saw that when this was a positive charge and this was a negative charge, the spheres came closer. So this is the distance between the center of the spheres, which he called as R. Okay, this was called as R. So when this was positive and negative, he saw that the force with which Q2 came closer to Q1, that is when they got attracted to each other, was directly proportional to the product of the magnitude of the charges. What do you mean by product of the magnitude of the charges? He saw that if let's say first the charge on each was plus 2 and minus 2. So he saw that now next he charged it to plus 3 and minus 3. He saw that initially they attracted together with a force of 4 Newton. Okay, minus 4 Newton. Second, when you increase the charges like 3 and 3, the force of attraction between them was measured to be minus 9 Newton. So he saw that the product, the force with which they attracted each other or repelled each other or moved away, suppose this was plus and this was also plus, with which either of them moved away from each other, that is this either moved away from each other, was also equal to the product of the magnitude of the charges. So it depended on, if you multiply them, you see that the force with which either they attracted together or moved away from each other was directly proportional, was same as, almost same times as the product of the magnitude of the charges. Now he wanted to also see how the centers, how the distance of the centers varied. When they are closer together, how did it vary? When they far apart, when they are far apart, when they moved apart, when when they were charged equally. He also wanted to measure how did F, the force of repulsion or attraction, varied with the distance between the center of the spheres. Okay, so he plotted a graph. Okay, he saw that force versus distance of the center of the spheres. Now he saw that there was a decrease when you decrease in the force when the distance moved away. Obvious, right? So when the so it happened. It was not a linear decrease. In fact, it was decreased as the square of the distance. That means the force of attraction or repulsion decreased inversely as the square of the distance and not just the distance. What do you mean by square of the distance? So initially, let's say if the distance between the spheres was 2 centimeters. Now when you square it, it becomes 4. So what happened to the force of repulsion? The force of repulsion was 4 times stronger. So now when if if they moved apart by 3 millimeter or whatever, so if it is 3 square, 1 by r square, so the force of repulsion or attraction next times was 9 times the force. So he saw that the force of attraction or repulsion varied inversely as the square. So it varied inversely as the square of the separation between the center of the spheres. So he combined these two equations. This is equation 1, where how the varied with the product of the magnitude of the charges, and also how it varied inversely as the square of the distance of separation of the centers of the spheres. And then he combined these two to come or arrive at an equation. When you combine them, this goes to the numerator q1 q2 divided by r square, and he introduced a constant called Coulomb's constant, which is denoted as k. That will be k into q1 q2 divided by r square, and this law of attraction is what is known as Coulomb's force law of attraction or repulsion in electrostatics. I hope it's clear. If you have any questions, you are always welcome to drop more comments so that I can do more videos on the same concept if it's not clear. Well, now it's time to state Coulomb's law in electrostatics. The Coulomb's law in electrostatics basically gives you the force of attraction or repulsion between any two charged spheres or any two charged objects. So how does this force of attraction or repulsion between any two charged bodies vary? He said that it states the force of attraction or repulsion. So this is very important from your examination point of view. You might get it for a mark. So the force of attraction or repulsion between any two charged bodies, varies directly as the product of the magnitude of the charges varies directly as the product of the magnitude of the charges. Why do I say magnitude? Because charges do not have direction. Charges are scalar quantity, so I say that it is the magnitude, product of the magnitude of the charges, and inversely as the square of the distance between them. And you cannot stop it right here. You should also say where does the force of attraction act, because you have to specify the direction in which the force acts, because force is a vector. Please always remember this. You cannot state it right here and stop it, then you are going to definitely lose a mark. You must specify the direction in which the force acts between the two bodies, either the repulsive force or the attractive force. So we continue the sentence and say that, and acts along the line joining the charges. Acts along the line joining the two charges. This is a complete statement. Only then you get complete marks for your board examination. So what does it say? Suppose if you have two charges, point charges Q1 and Q2, then this is the line joining the two charges. They are separated by a distance r. Then the force varies directly as the product of the magnitude of the charges, and it also varies inversely as the square of the distance between them, right? And it acts along the line joining charges. So if it is a repulsive force, see the charge force due to 1, force on 1 due to Q2, force on Q2 due to Q1 will be acting along the line joining charges in opposite direction if it is a repulsive force. If it's an attractive force, they act along the same direction, right? So you have to specify the direction of force. Please remember, do not leave it, okay? Now if you introduce a constant, I told you it's a Coulomb's constant, so I will rewrite it, I'll erase it, I'll rewrite it. I hope this part is clear. Okay, so we will rewrite it as F is proportional to Q1, Q2, product of magnitude of charges, also inversely proportional as the square of the distance between the charges. When you combine them, okay, you can call it equation 1 and call this as equation 2. Combining equation 1 and 2, we get F is proportional to, in the numerator you get the product of the magnitude of the two charges divided by the square of the distance between the two charges in the denominator. Introducing a constant called Coulomb's constant, you call it as K into Q1 Q2 divided by R square. Now, what is the SI unit for force? It is measured in Newton. K remains. What is the SI unit for charges? Charges are measured in Coulomb. So this is measured in Coulomb. This is also measured in Coulomb. This is measured in meter, but you have whole square. So what will be the SI unit for Coulomb's constant? Coulomb's constant will have a SI unit as K is equal to, let's cross multiply meter square here. So therefore this will become Newton meter square, and Coulomb into Coulomb becomes Coulomb square, it goes to the denominator. So Newton meter square per Coulomb square. So it was experimentally found that the value of K is 9 into 10 to the power of 9 Newton meter square per Coulomb square. Also K can be written as 1 divided by 4 pi epsilon naught, which is nothing but this. What is epsilon naught? Epsilon naught is the permittivity of free space. Okay, now since there is a word called permittivity, I need to explain you that we assume that the two charges, the force of attraction or repulsion between any two charges kept in vacuum. That is the sentence that I missed. So that's a must, because we are assuming that it was kept in vacuum. We are assuming that there are only two charges. One is Q1, another is Q2. In between Q1 and Q2, there are no other charged bodies at all. Because if there are more charged bodies, so if you have some other medium like air, water, it could be metal, it could be wood, it can be anything else. So if there is some other material between the two charges, then you will have to take into account the charges of that medium also, right? So what I mean is, if you have Q1 and Q2, we assume that they are separated by vacuum. There is nothing in between them. There are no air molecules. Assuming in an ideal situation, there must be no molecules between them. Only then we define this force law. If there is a medium, then it becomes complicated. So that is what is permittivity of space, and that value is given by, I think it is 8.854 into 10 to the power of 11. So that what will be the value of K, because it will be reverse of this, right? K, because K is 4 pi, epsilon naught will be equal to, if that comes here, it will be 1 divided by 4 pi K. What is K? K is Newton meter square per Coulomb square. So that will be 1 divided by Newton meter square per Coulomb square, which means Coulomb square goes up. So this will be 8.854 into 10 power 12. Coulomb square goes in the numerator divided by Newton meter square. So these are all very important questions. You can be asked to calculate the SI units for permittivity for K. So what I did was I used this equation because I knew the SI unit for this. I brought K here and epsilon naught here. So it becomes epsilon naught is equal to 1 by 4K. We already know it is K is Newton meter square by Coulomb square. So this goes to the numerator and this remains in the denominator. I hope this part is clear. So there was an error. It is not 10 to the power of 11. It is 10 to the power of minus 12. So this is 10 to the power of minus 12. Please make a note of it. That was an error. I have corrected it. So that is the value of permittivity of free space. Well, since force is a vector, we can express Coulomb's law in vector notation. In fact, that's the right notation because we are talking about a force between two charges, and force being a vector which has both magnitude and direction, it is essential that we write direction as well. So how do we do it? In order to understand that, I want to introduce how do you add vectors or how do you subtract vectors. So first let's understand that, and then it becomes really easy to write Coulomb's law in vector notation, because sometimes in your examination you might be asked to specifically state and write the Coulomb's force formula in vector notation as well. So please pay attention here, okay? Yes, so let's assume that this is some position O. With this position there is a point charge Q1. Why am I calling it a point charge? Because probably the distance between the charges is too large such that the size becomes very negligible. So there is another charge here and I call it as Q2. So the distance, this is the origin from where I am seeing. So this is the position vector. So position vector is from the origin to the charge, and I call this position vector as R1. That is the which points toward, position vector is a vector that points towards a particular point, right? It's to a position. So this tells me the position of Q1 with respect to the origin O. So position vector's job is basically to tell the position of a particular object. So what is the object here? The charge Q1. So Q1, if I randomly say, can you tell me what is the position of Q1? It becomes, it is somewhere there on the board, to the left side of the board, not to the corner, somewhere. I can't really measure it. I do not have a measurement. So what do we do in such cases? We choose an origin, and from that origin we draw a line pointing towards the charge, and we call such a vector as the position vector. So that tells me that it is at a distance R1 in a direction of R1 from the point O or the origin O. So even here I point R2, I call this as vector R2, which is pointing in the direction of the charge, right? Now I need to define this, right? So now what I will do from here to here, now when the line goes from this and the ends on this point, it is going from charge 1 to charge 2. So if it is going from charge 1 to charge 2, since it is going to charge 2, I write charge 2 plus two first and then 1, and I call this vector as R21. When I write R21, it doesn't mean it's a line joining or the arrow is pointing towards Q2. Since the arrow is pointing towards Q2, I write 2 first, then 1, because it's a line pointing from Q1 towards Q2. Therefore, this vector is what is known as R21. I hope that point is clear. I repeat, why do you write it as R21 and not R12? Because this vector or this vector which is represented by an arrow mark is pointing towards the charge Q2. Therefore, 2 has to be written first, and then it tells you it is pointing towards 2 from 1 to 2. So now when you have two vectors like this, going like this, and this is called the resultant vector. So this is the resultant vector. So how do you add? This is called triangle law of vector addition. So when you have two vectors, what is this vector? Vector R1 plus what is the next vector in the same direction? Vector R21 will give you the resultant vector, which is vector R2, right? So therefore, now what will be vector R21? Vector R21 will be equal to vector R2 minus vector R1, because when this goes on this, plus sign becomes minus sign. Similarly, if I have, this is R2, which was the earlier vector pointing towards Q2, and this is R1 pointing towards Q1. Suppose now I want to draw from 2 to 1, since it is going towards 1, I write 1 vector pointing towards Q1 from 2, which will be R12. So these are in this moment, circular. It goes from here to here. So this becomes the resultant vector. This is the resultant vector. So how do you write it? R2 vector R2 plus vector R12 will give you vector R1. So what will be vector R12? Vector R12 will be equal to vector R1. This has plus sign. When it goes on the other side, it becomes minus. So vector R1 minus R2. These are very important. You will need it especially when we are solving problems in further classes, electrostatics, also in scalars and vectors, also in a lot of MCQs. So please remember, vector R21 is R2 minus R1, R12 is R1 minus R2. When do you call it R12 and R21? You call it R12 when it is pointing towards 1 from 2. When it is pointing towards 2 from 1, you call it as R21. I hope that part is clear. Now, the very important point, now you know how to write these. How do you write the magnitude of this vector? So, the magnitude of this vector can be written within straight lines. So, when you write it within straight lines with an arrow mark, or this can simply be written as R21, that is also the magnitude of the vector without the arrow mark and without the straight lines. Then how do you write it? It is written as R cap, which is the unit vector, which means if it is, let's say if the vector is about 50 centimeter, then R cap will be 1 centimeter. So you are taking a unit vector, 1 centimeter divided by the magnitude of the vector. So it is, you write the direction, this will be equal to, how do you write the direction? R21 will be equal to direction of the vector divided by the magnitude of the vector, or you simply write it as unit vector divided by R21 instead of writing the arrow mark and within the modulus sign or within these straight lines you can also write. So direction can be written like this. Similarly here, what will this be equal to? This is R12 vector will be unit vector, right? What is the unit vector? You have to write unit vector as R21, even here it is R21. Unit vector R12 divided by the magnitude of the vector. So you can write it within the modulus or simply write it as R12 divided by R12. So that is how you write the direction. These are also very important points. You might feel, it is a lot to remember, a lot to practice. Practice is only the key. Don't be scared. Okay. So the more you practice, the more you write. When I say practice, don't by heart it. Don't just read it. You have to take a book. You have to take a pen. You have to take a paper. Practice it more and more so that it gets etched in your brain. And the more numericals we start solving, I'm also going to take up numericals from NEET, various MCQs, IT, JEE. I'll make more and more videos on that, and then it becomes really easy. The more you practice along with me, you feel it's so easy. Okay, that's the key. Well, now how do you define this Coulomb's law in vector form? In order to define or write it in the vector form, so we simply write it as vector F is equal to Q1, Q2 has magnitude. It doesn't have any direction, so it comes like this. So since this is R square, so we write it as R square into unit vector, that is R cap. Now suppose if you have to write it for F12, this will be F12 will be equal to Q1 Q2 divided by, it will be R12 whole square into multiplied by, you have to write the direction. For direction you have to just write the unit vector. It doesn't alter anything because the value is always 1. Similarly for F21 we write it as Q1 Q2 or Q2 Q1, it doesn't matter because you are multiplying, into divided by R21 the whole square into R21 unit vector. This value is 1 only, so it doesn't alter anything. So this is how you write your unit vectors. or this is how you write your Coulomb's law in vector notation. It becomes really easy. Okay, now it's time to define something called 1 Coulomb. So how do you define 1 Coulomb? Imagine this is 1 Coulomb. Okay, so we define 1 Coulomb as, I better write it down so I know it becomes really easy. I'll erase this part and write it down. So let's define 1 Coulomb. What is the definition of 1 Coulomb? It's a very important 1 mark, numerical, or it can be there for MCQ. So 1 Coulomb is defined as the charge is said to be 1 Coulomb. The charge is said to be 1 Coulomb, which when placed from another charge, which when placed from another charge, another similar charge, so which means you are placing it with another 1 Coulomb charge, similar charge. Where are you placing it? You are placing it in vacuum. In vacuum, this is important, I missed it earlier. In vacuum, okay, experiences a force of attraction which when placed in vacuum at a distance of 1 meter, experiences a repulsive or attractive force, equal to how much? 9 into 10 to the power of 9 Newton. Why? Because this is the value of K. How did I get this? F is equal to K into Q1 Q2 by R square. So I am calling this as 1 Coulomb. So this will be 1 and this will also be 1 meter. So K, when is F equal to K? This charge will be equal to 1 Coulomb if they are separated by a distance of 1 meter. So this is also 1 Coulomb, this is also 1 Coulomb. So charge is said to be 1 Coulomb if a charge of 1 Coulomb is placed from another charge, similar charge, in vacuum at a distance of 1 meter. Then what force does it experience? It experiences a force equal to K. What is the value of K? K is 9 into 10 to the power of 9 newtons. So that is how you define 1 Coulomb. Well, now let's talk about Coulombian force of attraction or repulsion, not only due to 2 charges, but what if there are multiple charges? Let's say there are not only 2 charges, there could be hundreds of charges, there could be, how each charge, force of attraction or repulsion between 2 charges will affect. How are you going to find the net force of attraction or repulsion? In order to do so, let's make an assumption that there are, charges like there are Q1, Q2, Q3, etc. up to Qn. N can have any number starting from 1 to 100 or whatever, let's say, right? It can have any number. It can be 1000 charges, a million charges, it can be any number of charges. In such a case, well, how would it look like? In the first case, I have to assume origin, right? So I'll assume only 3 charges. So I'll call this charge as Q1, so this will be obviously R1. I'll call this charge as Q2, I'll call this charge as Q3. Okay, so this will be R3, this will be R2, that is the position vector which tells you how far away is it from a particular origin. Well, now how do you calculate this? If you have 3 charges, there could be n number of charges, but for example, I have only taken 3. In such a case, how do you find out the effect? So there is 1 charge here, 1 charge here, 1 charge. Each charge will exert a force of attraction or repulsion depending on whether it has a positive charge or a negative charge. So can you think how do we find out? I'll give you a minute to think and then I'm going to explain this. Okay, so now let's make an assumption. I hope you got it. So since this is R1, since this is, this vector is acting in this direction, in order to find the resultant here, I will call this as pointing towards 3 from 1, this becomes R31. Suppose imagine this is also a positive charge, this is also a positive charge. So what will happen to the charge here? It will move in the opposite direction. So this force, which is F31, force on 3 due to 1 will act in this direction. Similarly, suppose this is Q2 and this is R3, right? So if I take this will be the charge, this is acting on 2 due to 1. So what will happen to the charge? This is positive. If this is also positive, it will act in the opposite direction. So I am not taking into account on Q3. So what will be the resultant of this force will be called as, what will you call this force as? 2. It is acting on charge 3 due to 1, so it will be due to 2, so it will be F32, right? So what will happen in such a case? We use a law called parallelogram law of vector addition. So you complete the parallelogram, you have two sides. You complete the parallelogram. The diagonal of the parallelogram is what gives you the net force acting on charge Q3 due to Q1 and Q2. So I am only finding out the charge on Q3 due to Q1 and Q2, right? So if that is not clear, I will write it here again in a bigger sense. So this is charge Q1. Okay, there is another charge Q2 here. Let's write it here. This is Q3. So here is here is another charge Q2. So there are these two charges are acting, you have to find out what is the net force on Q3. So what do you do? So initially first you write the position vectors. Call this position vector as R1. Call this position vector pointing towards the charge 3 as R3, towards R2 as R2. Now, so suppose this is also a positive charge, all of them are positive charges. So the line joining from 1 to 3 is the position vector pointing towards 3 from 1 is called R31. Similarly, since both are positive charges, this charge will experience a force of repulsion in the opposite direction. So this is the force experienced by charge 3 due to 1. That is why I represent this as F31. Similarly, this will also exert some force. So if this is the force, so this is called the force exerted on 3 due to 2, right? Charge 3 experiencing a force due to 2. This is also positive, so therefore charge Q will also experience a force of repulsion in the opposite direction. So it is like somebody is pulling it here also, somebody is pulling it in here, this direction also. This is the force experienced by charge 3 due to charge 2. Now in such a case, how do you find the resultant? You use a law called parallelogram law of vector addition, where you complete the parallelogram using the two sides. You draw and assume other two sides and draw a diagonal pointing towards one corner, and you find out this net. You will also find out these angles, okay, and using that you calculate the net force acting on charge Q3 due to charges Q1 and Q2. Okay, I hope this part is clear.